Hi everyone, welcome to the colloquium, and in fact the last colloquium of the term. Happy that everyone made it through the snow to get here today. Very happy to introduce Tutte-Euiwoong Lee, who is an assistant professor at the University of Michigan. So he got his PhD from Carnegie Mellon University, was a research fellow at the Simons Institute in Berkeley, and a postdoc at New York University. So his research is in several topics of computer science, including approximation algorithms, and the hardness of approximation, and has won several awards, including an NSF Career Award, the Edmund M. Clark Dissertation Award, and the iCalc Best Student Paper Award.
Thank you. Thank you for having me, even with a very last-minute request. So I gave a talk last year's June. I'm happy to give this talk again. Not the same talk. And then today I'm going to talk about this optimal hardness for k-set packing and related problems. And then this one is the two papers. The first one is with Pasiman Rangsi, and then we gave some hardness result for generalization of this k-set packing problem. And then this year we had a paper with Theo Thieri and Ola Svensson proving the hardness of a special case of k-set packing. So at least we covered k-set packing and then slightly more problems. Okay, but then let me tell you some story about k-set packing problem first. Okay, so it's one of the very natural optimization problems. Okay, so input is a set system, or like hypergraph. The U is a universe, the set of elements, and they're we have M subsets. And then we are assuming that each subset has size at most k. And then, so the role of k, I think, will be like this in this talk. So k will be constant with respect to running time. So I think we are ruling out the algorithms of running time like n to the k or like n to the 2 to the k. So from the running time perspective, k is constant, but then we will express our approximation ratios as a function of k. So that's what the k role of k in this talk. And then of course, I think the goal is to choose the maximum, the collection of these the subsets that are pairwise disjoint. Okay, just in terms of hypergraph, just computing matching. Okay, that's why some people call it just a hypergraph matching problem. And then, of course, when k is 2, then it exactly becomes a graph matching problem, which has a lot of ties to the University of Waterloo. Okay, so this is an example of a 3-set packing instance. And then if you can look at this instance, and then actually there's a very good solution. Actually, color is not very good. Okay, it is these 3 sets form a perfect packing. So the optimal value is 3 here. Okay, so problems are very fundamental basic problems. And then, okay, so then what is known about this the k-set packing problem? Okay, so you can easily say that one can get k approximation for unweighted hypergraph, then one can easily say that any inclusion-wise maximum packing will give you k approximation, because if you have one hyper edge in your solution, then it can kill at most of the k edges in the hypothetical optimal solution. And then for the weighted setting, it can be slightly more complicated, but then you can just it can be achieved by some LP-based methods like primal dual or just LP rounding and stuff. Okay, so then can you do better than k? Better than? No. Yeah, can you do better than k? I think the answer is yes. And then it's a somewhat interesting algorithm. Okay, so at least let's start from the unweighted case. Unweighted means that each set has a weight 1. Then actually the very nice local search algorithm can guarantee you k over 2 approximation. So this was observed by Herkins and Schreiber. And then this the with 2 local search means that what the algorithm is doing is trying to maintaining some feasible solution, some matching, and then it's trying to find the possibility of removing one edge from my collection and then adding 2 edges instead. If such a solution exists, then you just go to that solution, and then you just do it again until you can't. And then until you can't, then actually the outcome is called the local optimum. And then they prove that that's going to be exactly k over 2 approximation. Okay, I think I'm going to ignore this the additive constant after k for the rest of the talk. So I think we are focusing on this the multiplicative factor for k. Okay, but then actually analysis is very simple because one can see that okay, so let's fix our solution alg, which is local optimum. And then, of course, then one for any set that I found, then I can define the degree of this my set, which is just the number of optimal sets that intersect. Of course, I can intersect with at most k optimal sets. And then I can do the same thing for optimal solution. For every opt set, I can define the degree to be the number of sets in my solution that intersect. Okay, so then, of course, they should be at most k. But then one observation one can make is that if I fix one set that I found, then of course it's gonna intersect with at most k optimal sets, and then they will have their like own degrees. But then one can easily observe that my set S will intersect with at most 1 degree 1 offset. Because if I look at one set I found, and then if there are like 2 sets of degree 1 intersecting with me, so then it means that there is like the valid local move, meaning that I can just remove this set from my collection, and then adding these like the 2 optimal sets that has degree 1, meaning that it doesn't intersect with any of the other like sets in my collection. Okay, so yeah, so it means that one can observe that every set intersects at most of 1 degree 1 offset, meaning that, okay, so then like apart from that guy, most of the offsets have a degree 2 at least. Okay, so then it's kind of doubly counting argument. Okay, so my sets are intersecting at most k, and then the other sets are intersecting at least 2. Okay, so that the ratio between my sets and the optimal sets should be at most k over 2. Okay, so that was like a very simple k over 2 approximation. And then the k over 3 approximation can be done as well. And then one naive way to do is with order log n. Okay, so then how we do it? It's the same kind of business. But then, since we already kind of dealt with the degree 1 offsets, let's try to bound the number of degree 2 offsets. Okay, so if you want to do this, so then I can think about the graph, where like vertices are like my offsets, and then edges are like, I'm only looking at degree 2 offsets. And then if I just look at the degree 2 offsets, then I can just draw them as edges of the graph. Okay, so this is my graph. Just portraying this degree 2 offsets. And then if these degree 2 offsets is larger than my number of my sets, which is the number of vertices, so then this graph will have more edges and vertices. Okay, so then this thing called the Moore bound is saying that, okay, so if the number of edges is like 1% more than the number of vertices, so then there will be a log n length cycle, probably like with at least 1 chord. Then that log n length cycle with 1 chord will be on the possible move. Okay, because the vertices are just the by offsets, and then the edges are exactly the offsets that I can improve with. Okay, so this means that if our solution is a local optimum with respect to like order log n width. Okay, so then actually even though one can even bound the number of degree 2 offsets. Okay, so then apart from the degree 1, degree 2, then everyone else should have a degree at least 3. So then the same double counting argument basically tells us that the ratio is again I intersect with at most k, and then you intersect at least 3. So the ratio between them is at most k over 3. Okay, so that's a very kind of simple k over 3 approximation, at least in the unweighted case.
So how do you find an improving move here?
So improving move is just like try every like log n vertices here. So so log n length cycle with 1 chord is gonna give you like is an improving move.
So I guess that's for the analysis, but I'm saying for implementing this.
Yeah, so it's a quasi-polytime.
Okay.
Yeah, at least okay, good. Yeah, so this paper, like first paper, is a quasi-polytime algorithm, and then Sigang's paper actually improved it to polynomial time by considering like not just every possible move, but then like kind of looking at the very special kinds of moves.
And the weight is the same for the polytime algorithm?
Say again?
So for the polytime algorithm that you mentioned, you also look at moves of width log n?
I think it's inspired by this, but then I think they do smarter things. It's not exactly looking at every possible log n move. Okay, so that's like k over 3, which is like still the best approximation ratio for unweighted case. And then the weighted case, actually it's even the k over 2 is not clear. And then one like non-trivial algorithm is a k over 2 approximation by Berman. And then their method is non-oblivious local search, in a sense that now like instead of the same local search, but then instead of trying to maximize the number of sets, which is like an objective function for our problem, it just like sets, it just defines another another objective function, or like can be called the potential, and then tries to make a local move that strictly increases the value of the potential. And then somehow, yeah, if you have a local optima with respect to that potential, then somehow like they analyze that, okay, that's gonna be k/2 approximation for any problem, okay, which is kind of magical. And then recently there was like some attempt to like beat this k/2, and then they did, but then at the level of just additive constant. Okay, so it's still like k/2 is asymptotically the best approximation for a weighted problem. And then, yeah, but then of course, local search is a very nice algorithm, but then if you're like studying approximation algorithms or combinatorial optimization, then you always want to like have some polyhedral understanding, or like some understanding based on relaxations. So then, yeah, then one natural attempt is to kind of at least design like more convex relaxation-based algorithms capturing part of these local search algorithms. And then, yeah, there's like a very nice paper by Lapchi exactly asking these questions. But then actually the answer is like has been like not very like satisfactory from the combinatorial side. Actually, surprisingly, he proved that even like linear number of Sherrill Adams hierarchy, I think it's gonna have a gap at least k-2, so it almost does nothing. And then they proved that STP relaxation has a gap of k/2. But then it's not still clear whether like there's the relaxation-based method that even captures a k/3, which is not really hard. Yes, I think at least perhaps it's not really related to like getting a better approximation algorithm, but then one problem I really like is that even like log n rounds of sum squares. I mean, suppose that I find it a quasi-polytime algorithm. Okay, so can they capture this the k/3 approximation? I think that's like very like interesting question, yeah, by itself. Okay, so these are algorithms, and I'm going to talk about the hardness. Any questions here? Good. Okay, and then I just talked about k-set packing, but then it has like many other problems related to k-set packing. Okay, so yeah, one special case that we are actually going to prove hardness for is this thing called the k-dimensional matching. Okay, so it's just in terms of a hypergraph, it just means that hypergraph itself is a k-partite. Okay, so universe is the disjoint union of k-sets u1 through uk, and then each the set has exactly one element from each ui. Okay, so that's a k-dimensional matching. Then of course it's a special case of k-set packing, but then now it's nicer because one can view this as a special case of a k-Matroid intersection. So the intersection of a k-partition matrix. Okay, and then of course if you view it as a matrix intersection, then I think there are like many matrix-based generalizations. I think this is one diagram showing the hierarchy of these problems. But then another problem, which is like not slightly not in this like main line that we first proved the hardness for, is a distinct problem called the independent set in d-Clawey graphs. Okay, so this is like this the problem here, and then one can kind of see that this is a generalization of the d-1 set packing, because if you just have an instance of a k-set packing, and then if you just look at this graph representation, where like each set becomes a vertex, and then if you like connect these vertices, if they intersect, so then one can see that this is this will not have a k+1 claw, because if I'm one set, and then if I have if I look at k+1 of my neighbors, but then like my neighbors mean that they share an element with me. So if I have a k+1 neighbors, then there exists like the two neighbors that share the same element with me, and then these two guys must have an edge between them. Okay, so this shows that the graph representation of k-set packing will not have k+1 claw. Okay, so that's why the claw-free independent set is a generalization of d-1 set packing. Okay, so and then so it's a slightly more general problem, but then actually the most of the algorithm I told you that in last slide work. Probably the exception is that k/3 still needs quasi-polytime, because like the previous k/3 polytime algorithm really like was specialized for set packing. Okay, but anyway, those are like the problems we're going to study, especially k-dimensional matching, because like that's and then the independent set in k claw-free graphs. Good. Okay, so then our like main result is following hardness. So the previous hardness was the order k over log k. This one is by Hazen, Safran, Schwartz. And then our result is a kind of asymptotically optimal hardness for these problems. So first, we proved that there's no like k-over approximation for k-set packing, or like k-dimensional matching. And then, yeah, in the actual first paper with Manrangsi, we proved that for D cluster independent set, the ratio can be slightly higher, so it's going to be D over some 5.8. So that was like what we wrote in the paper. But then, even then, yeah, the kind of similar, the same approach can be like strengthened if you assume like some more like stronger complexity hypothesis. For example, unique games conjecture. Okay, so if you assume unique games conjecture, then yeah, we would have got like k over 8 for k-set packing, d over 4 for like D cluster independent set. Okay, so of course the unique games conjecture was not proved, but then there's a very nice work of Minzer and Zhang. Basically bypassing unique games conjecture and then just prove this, got this the hardness numbers, k over 8 for k-set packing, and then d over 4 for independent set. Again, the same assumption that NP is not contained in polynomial time. Okay, and then yeah, I'm gonna show you the hardness, but then you can kind of see that this 8 and 4, like it's kind of the best thing you can get, at least using this framework. Okay, so it's yeah, so it's quite good, but then probably it's going to be hard to improve, at least using the similar ideas. Okay, so that's our like main result. Okay, so then yeah, let's go to like some technical details. Okay, so good news is actually they're extremely simple. I think the proofs are like at most 5 pages each, or like probably one can compress to 3 if needed. And then I'm gonna try to like tell you the entire proof of like both papers, so it's a great bargain. And then I think there are like 2, I mean, still like it's very simple, but then if I just try to really extract something, then there are like 2 conceptual viewpoints. First one is a kind of more like significant. So we achieve this hardness by looking at this thing called the constraint set exclusion problems with bounded degree and bounded alphabet assumptions. Okay, so I think a bounded alphabet is something that hardness people really studied a lot. So I think this one, and yeah, we are going to borrow them as a black box. And then actually that's what the paper of Minzer and Zhang was about. Okay, so this was like bounded alphabet. It was like the center of study from the PCP literature. But then bounded degree, I think this one was kind of like kind of niche. Some people thought about it, but then not optimally. So I think this one we kind of like tighten them up. And then of course, and then no one thought about this bounded degree and bounded alphabet at the same time. Instance having like both term restrictions. And then somehow like having like both restrictions was like crucial for our reduction, as you will see. And then the second, embarrassing viewpoint is like kind of just the maximally squeezing Chernoff bound. I think I'm going to tell you more. I think there's some story behind it. So then there are like the 3 parts to the rest of the proof. So the hardness of CSPs. And then starting from there, then you can just use this to hardness of a cluster independent set and hardness of a k-dimensional matching. So I think let's just proceed in this order. Okay, so let's just start with the CSPs. Okay, so let me just start by defining CSPs. It involves like some notations which are like not very necessary, but then let me just do it. Okay, so I'm gonna name them A CSP. Normally, I think CSP, people call it K-CSP, where like the K is arity, meaning that each constraint depends on like K variables. But then of course, like K here is K is taken, so let me just use A, where like the A means arity. Okay, so but then in this talk, A will be like 2 or 3 or 4. So I think, so A CSPs. So input is the set of n variables, x1 through xn. And then the alphabet or domain, the set of values where like each variable can take a value from. And then we have m constraints, and then each constraint will be represented by a ci and phi, where like the ci exactly points to the a variables that the constraint will be applied to. And then the phi is the set of accepting strings. Okay, so a set of strings that will make this constraint satisfied. And then, so that's the entire input. And then there are like 3 parameters here. Okay, so A is the arity, and then R is the alphabet size, and then the D is the maximum degree. Just if you fix a single variable, then how many constraints contain this guy. Okay, so those 3 will all play a role. But then the role of them actually in this context will be the same as usual. Computationally, I think we'll treat everything as a constant. But then, yeah, for approximation ratios, I think we will like, again, express them as a function of R and D. And then A, which will be like 2 or 3 or 4, will only be hidden in the big notation, if they are hidden.
So I don't ask, what does it, everything is constant, N on M, or no, just those 3 things?
No, just 3 things, yes, yeah, A, R, D, yeah. Good. Okay, so then, yeah, goal is to find an assignment that gives a member of the sigma to each variable to maximize the number of satisfied constraints. Yeah, so this can be formalized in this way. And then given an instance I, let me define opt I to the normalized optimal value for the instance, which is between 0 and 1. Okay, so that's all standard notions. And then, of course, like this is a hardness talk. So let me just define a notion for hardness. Okay, so we're going to say like A, CSP, RD is a CS hard. So now like there are 5 layers. If under like some reasonable assumption, no polynomial time algorithm can distinguish whether like the optimal value is greater than C or less than S. Okay, so I think yeah, let's because I just want to like use short letters for like the hardness. Okay, so that is that's our definition of hardness, and then we want to establish like some CS hardness for like some CSPs. Okay, yeah, so that's the definition. But then good thing is that I think for us like C will be always 1 minus epsilon. C will be always, we will only consider the C value which is like very close to 1. Okay, that's so 1 less letter. So then the question is, okay, so then what's the smallest value of S given A, R, D so that the hardness still holds? So I think that's going to be the question that we're going to study, at least for the CSPs. And then if you think about, so I told you like the bounded R case was actively studied from the complexity theory side. Okay, so then yeah, what can you say about bounded R? Okay, ignoring what D is. Okay, so of course, yeah, one thing one can say is that S should be at least 1 over R to the A, because even if it's just like random assignment. Okay, so one constraint, yeah, there are like R to the A possible strings, and then yeah, random assignment will satisfy at least 1 of them. So that's this one is trivial. And then actually, well, it turns out that one can subtract 1 from the exponent. Okay, so this is just coming from the fact that if A is 1, then it means that every constraint depends on only 1 variable. If that's the case, then yeah, for each variable, you can at least do the greedy algorithm to solve the problem optimally. And then this kind of simple idea can be generalized to like general A to at least like subtract 1 in the exponent. And then actually the best known algorithm is not very far from that. Okay, log R over R to the A minus 1 is our best known algorithm. And then hardness, I think, yeah, it was long story with a lot of work. But then, yeah, the aforementioned work by Minzer and Zhang actually give you almost the best, almost optimal hardness. Okay, over 1 over R to the A minus 1 minus epsilon for any constant epsilon greater than 0. Okay, so basically, yeah, 1 over R to the A minus 1 is like the the approximation threshold for bounded R, which is just completed this year. Okay, so what about bounded D? Okay, so for like however large R is. Okay, so yeah, one can at least 1 over AD is kind of trivial. The algorithm may be just find the maximal set of constraints that are completely disjoint. Okay, so then you're going to get at least 1 over AD fraction of the constraints because having one constraint will kill at most A times the D other constraints because area D is A and then the degree is D. And then at least if you have a disjoint constraints, then you can just satisfy just them to get the 1 over AD approximation. And then of course this simple idea can be slightly made smarter when A is 2. Because what one can do is that, okay, so that if A is 2, then the constraint graph is just a graph. And then what I can do is just take a kind of spanning tree and then solve the spanning tree using dynamic programming. Okay, so this one you can do. And then if you take a spanning tree, then the number of edges will be exactly, or like at least 2 over D fraction of the total number of edges. Okay, so that's 2 over D. So then you can see that 1 over D still is kind of the right ballpark at least up to low factors. And then hardness, I think, like Kanuk's work, at least proved the hardness of log t over t when A is 2. But then even that, I think, again, that this was not a very well-studied regime. And then actually, we at least proved the hardness of A over A minus 1 times t. Okay, so one can see that if A is 2, then actually this is, matches 2 over t approximation. Okay, so yeah, at least you're going to see that hardness for bounded t as well. Okay, yeah, so that's what we're going to do. And then, yeah, and then let's try to see how to get the hardness for bounded t, or like some more nuanced regime that we're going to be using for set packing. Okay, so then our starting point will be this one, the hardness for bounded R, because like this was really well studied regime in complexity theory. So then our efforts to reduce the degree is kind of like the most natural thing you can try. Okay, so then we're gonna start from this amazing hardness for bounded R. But then, of course, if you look at this hard instance for like bounded R, then degree doesn't have any guarantee. Degree can be much large. Okay, perhaps I think what one can assume is that at least this is a regular instance. Every variable is contained in the same number of clauses. That one can do. But then this t value, the degree in the starting instance can be much larger than d, or it can grow with n. I don't know. But then, of course, then you get this instance, and then you wanna make it degree d. Okay, what are you gonna do? Okay, I don't know. Probably the only thing I can do is just sample each constraint independently with probability d over t to get the instance I prime. Okay, so so I set d over 2, but then you wanna set probably you shouldn't do exactly d over 2. You may wanna do like 1 minus epsilon times d over t because I want most of vertices have a degree at most t. So I think, in this talk, the approximation sign will denote the 1 plus minus epsilon multiplicative approximation for any constant epsilon greater than 0. But then, if you sample everything with probability d over t or like slightly less than that, so then one can easily see that, okay, so then most of vertices will have a degree at most t, or if some vertices degree exceed d, then I can just delete arbitrary edges. But then, one can kind of easily see that the number of such edges deleted will be small. So that we're going to ignore this step, and then that's a whole reduction. Okay, just starting from instance, just a sample with probably slightly less than d over t, and then if there's something goes over t, then just delete them to make sure that it's a degrees at most t. Okay, so that's entire reduction, and then now let's try to see like what we can argue about the soundness of the reduction, or like how this reduction preserves a gap. Okay, so at least the easy thing to do is just like arguing about the yes case. Okay, because if the starting instance has a good solution, okay, so then we are just like still random sampling, and there's only one solution to worry about. Okay, so then that solution will be likely to be good in the new instance as well. Okay, so it's going to be still like very perfect solution. And then of course like no case analysis is always the interesting part, but then again it's just a one-page analysis. Okay, and then the most standard analysis. Okay, so then suppose that we want to prove this. Okay, so assuming that the optimal value of the starting instance is at most gamma, my goal is to prove that optimal value of the new instance is at most gamma prime. Okay, that's what I should do. Then what am I going to do? I think I'm going to do this fixed one assignment. Prove that the probability that assignment is that assignment's value is greater than gamma prime is extremely small, then I'm going to take a union bound. So again, like very the most natural strategy. So like let's fix one assignment f. I know that at least in the original instance, it satisfies at most a gamma fraction of constraints. That I know. Okay, so then in this random instance I prime, so then f will satisfy at most gamma fraction in expectation because we are just at random sampling. Okay, then that's the term bound that I'm going to use. Okay, it's just like something that can be easily found in Wikipedia. Okay, so if f is some is independent 0 and variables, and then mu is our expected value, then for any delta greater than 0, the probability that x is greater than 1 plus delta times mu can be bounded by e over 1 plus delta to the 1 plus delta times mu. Okay, yeah, that's the version of general bound I'm using. Yeah, and then the crucial thing is that probably I think I mean, at least more well-known version, or like a weaker version, is like putting some constant here less than 1, and then 1 plus delta mu. I think this one is here, but actually somehow the fact that we can make even the base some sub-constant, I think it's what gives us like some power. Okay. So then if you just like plug this bound, then of course like 1 plus delta is exactly the gap between the what I want and then what I expect. Okay, so base will be E over gamma prime over gamma, and then the 1 plus delta times mu is exactly gamma prime times the dn over A. Okay, so that's and then now, okay, so that's the probability for one assignment, and then we want to battle this probability with this like the number of assignments, which is like n log r. Okay, so then yeah, that's the battle we are doing. Okay, so nothing is special here. But then somehow I think, at least in the literature, what people were missing or like didn't care is somehow the fact that we can make the base the subconstant, which is yeah, and then actually one can see that I was like I always liked this bound, so that even when I was like TAing as a second year grad student, I made a homework and then I kind of made this one exercise based on this term bound. Okay, so I did that 10 years ago, and then I kind of did it like even like 5 years ago as a faculty. Just again, yeah. So I always liked this bound. But then anyway, so then nothing here is fancy. Just the most the intuitive thing. So then with this with this the bound. Okay, so then we will get the gamma prime hardness as long as the gamma prime satisfies this bound. And then, yeah, if you just care about extracting the best hardness with respect to D only, okay, so then one can set, okay, gamma is going to be always 1 over R to the A minus 1. And then if you just take R to be much larger than D, then basically this term becomes A minus 1 times log R. Okay, yeah, because then one can ignore just the gamma prime. So that as long as gamma prime is at least A over A minus 1 times D, then actually then we get the hardness. Okay, so just yeah, the log R here just cancels, and then we just get the gamma prime and DNA. Okay, it's just and then yeah, and then and then for some reason that will be clear soon. I think we also needed to consider the case where like D is equal to R. And then yeah, if you let D is equal to R, then this expression, because the gamma prime will be like the order of R. So then this expression will be A minus 2 times log R. Okay, so then it's also same calculation, but then we get slightly worse hardness, which is A over A minus 2 times D. Okay, but then in both cases actually we get exact just even without losing a constant here. So we get exact hardness of some expression of A, more importantly 1 over D. Okay, so that's what do you do? Kind of most obvious thing. It's I don't know what else to tell. Any questions? It's just undergraduate probability class. Okay, so yeah, good. Okay, so then but then at least but then it's kind of like results are kind of nice. So then because like at least when the degree is bounded by D, then there's like at least the 1 over D approximate algorithm, at least for constant A, and then we are exactly matching this the 1 over D approximation, possibly even up to like constant factor depending on what A is. Okay, so that's pretty nice. And then let's try to use this to prove hardness for like the actual case attacking and related problems. Okay, so then let's try to first prove the hardness of the D Cloffer independent set. Okay, so which was the result of the first paper. And then again, this guy was so this reduction is like kind of one of the most classical reductions from CSP to the independent set, which is known as a FGLSS graph. Okay, so phi get Goldwasser Lovas, secondly, okay, sorry, I think I'm confused with this. But then, this is kind of one of the most the basic and the fundamental reductions from CSPs to independent set. Okay, so then suppose that now we have the hardness for like 2D Clough-free independent set. And then let me represent the constraint graph like this, okay, where like each square is a variable, and then each edge represents the constraint. So then, FGLS graph means that in our reduced instance, so then vertices will correspond to like each constraint and satisfying assignment pairs, which means that each constraint generates a cloud of vertices. And then like each vertex here corresponds to the one accepting string for this constraint corresponding to this edge. And then we put edges to two vertices if they, as a partial assignment, they like contradict. Okay, so they give the different values to the same variable. Okay, so that's the entire reduction. And then if you do this, okay, so then actually the well-known fact is that actually then this is exactly approximation preserving, or even the optimal value is exactly preserved. Okay, so because picking like one vertex from one cloud means that you are like committing to like one satisfying string for that constraint, and then whatever you picked must be fully consistent. Because if they are not consistent, meaning that if two assignments give different values to the same variable, then they're not going to be independent. Okay, so this reduction is just exactly the optimal value preserving. And then, of course, another thing to check is that this is actually a Clough-free graph. But then again, that is not very hard to see because if I look at one vertex in the final instance, which is suppose that this is one vertex, so then how many? It can have many neighbors because R is unbounded. So I think each cloud can be large. But then there are like only 2D minus 1 clouds that it can be adjacent to, because starting CSP instance has a degree D. And then of course, if you have 2D neighbors of this vertex, okay, so then since there are like 2D minus 1 clouds, then at least 2 vertices must come from the same cloud. And then, each cloud is a clique because they are like corresponding to accepting strings of the same clause, which means that they're all contradicting to each other. Okay, so this reduction easily tells you that each vertex, it's a 2D Clough-free, and then the hardness, which is like the D over 2, is exactly preserved here. So then you get D over 2 hardness for 2D Clough-free independent set. Okay, so if it's a D Clough-free independent set, then the hardness ratio becomes D over 4. Okay, so it's again, another like classical thing. Okay, so then the final thing is the hardness for k-dimension matching. So that one is slightly more interesting, but then even that, like I think we just took it from the existing earlier paper, or even simplified it. Okay, so then let's explore this slightly more slowly. So then again, this the gadget, So at least the good thing is that we can just proceed slowly. We can just look at the variable gadget level first, and then actually kind of piecing those gadgets will not be very hard. Okay, so let's first talk about the variable gadget. Okay, so again, it's following the idea of Hazen, Safar, and Schwartz. Again, let's consider this A CSP RD instance. So then for each variable x, I'm going to create this set system for this variable x. Okay, so again, there's a universe for x, and then there will be many sets labeled by I and j. So I is between R, 1 and R, and then j is between 1 and D. And then there are like 3 constraints for this sets that I want. Okay, so first one easy thing is that, okay, so I want each set has like size t, exactly. And then the second thing is that for if you fix R, and then if you look at the set of Xij's by varying j, sorry, I think it should be, the I shouldn't be here. So 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 then if you look at the D sets for fixed I, so then they should form a perfect matching. Okay, so I think that the way I visualize is I is a color. Okay, so then if you fix a color and then look at all the hyperedges of that color, then actually they form a perfect matching. Okay, so which is the case here. Okay, so if you fix a color blue, then yeah, blue guys form a perfect matching. And then if you fix red, then red guys form a perfect matching. Okay, so that's what 2 means. And then 3 just means that if you have like 2 sets of different colors, then they gotta intersect. Okay, I think which is not the case here. So I was figuring out, okay, because like this blue set and then this red set, those 2 are not intersecting. So it's a wrong example. But then that's what you want. Okay, so if you just the sets of the same color are like perfect matching, they're distinct from each other, and then the sets of 2 different colors actually they must intersect. Good. Okay, so yeah, and then of course it will be clear when we do the full reduction, but then at least in just trying to establish the connection between CSP. So basically what we will want ideally is that, of course, we want to use a set packing to solve CSP. And then what we want ideally is that the event that the variable x gets a value I, because like the I is exactly between 1 and R, the alphabet size. So then that event should be like corresponding to the event where we picked all the sets of color I in the matching. Okay, because yeah, now we can see that, okay, so if it's going to be like great, good if you're like consistent, and then if you're just like picking the sets of the same color. Okay, so that's what we want. And then then the question is, okay, so now we want to get hardness, but then given the same hardness, so then we want to minimize the set size, because like that gives you like better approximation ratio in terms of the given set size. Okay, so then of course we want to make sure that given this 1, 2, 3 requirements, we want to make sure that T is minimized. Okay, so then given R and T, if I give you this like the 1, 2, 3 requirements, so then how small can T be? Okay, so can you design a set system with the minimum T so that like the property 1, 2, 3 are satisfied? Okay, so that's a good question. And then if you look at this version of the question, then one can easily see that T must be at least D. Because even if I look at one set here, one blue set here, okay, it's a bad example. Let's look at the second blue set here. So then look at one color. Let's fix one other color, red color. Okay, so then what I wanted was that all these like the red sets, they are all disjoint from each other, but then they all have to intersect with me. Okay, so then it means that the size of me, the like width of this picture, should be at least the number of red sets, which is D. Okay, so T should be at least D there. But then for this earlier work by Hazan, Safra, and Schwartz, at least their framework was that because like they didn't care about the CSP with bounded degree. Okay, so they always started from the CSP with the bounded alphabet only. So then it means that they don't have any control over D. Okay, so it means that whatever they do, actually they gotta accommodate every possible D. I mean, D can be like, I don't know, N, or like 2 to the K. So, which doesn't make sense here. If you just record this 1, 2, 3. So then what they did is, okay, so instead of like requiring 3, so then just they just required some relaxed version of 3. Meaning that, okay, so if you just have a large match here, then like that matching better be like very close to monochromatic. Okay, so there's like more quantitative statement for like 3. And then that requirement made them, allowed them to like set T to be only a function of R, which is R times log R. And then with respect to their definition, actually this is tight. And then that's why they kind of was like losing log factors. Because like, they really fixed R, and then they wanted to prepare for every possible D, which kind of complicate the analysis, and then made them like lose extra like log R factor. Okay, that's what they did. But then for us, it's the same slide. but then for us, now we establish the hardness of the problem when R is exactly equal to D. Actually, I was gonna give you some keys, but then now it's, but then what can you do? Okay, so now like R is equal to D, and then I wanna get this like 1, 2, 3. Okay, and then the answer is just like the lines in a plane. Okay, so as soon as like we assume that R and D are like the prime powers so that we can define a field. So then our construction is okay. The I, the color, becomes the slope. And then once you fix the color, then the sets are exactly the set of all like the lines with that slope. And then one can see that, okay, then for each color class, they will exactly partition the entire plane. And then of course, like if you have 2 different colors, then they will intersect. Okay, so that's kind of the innovation of that's our very creative gadget. Okay, so but then that's it. Okay, so that's our like gadget construction. Okay, so now one can say we even simplified the number 3. Now like this, like number 3 is just good enough as it is, compared to their like previous number 3, which like kind of like it was kind of quantitatively more complex. Okay, so is this gadget good? Of course, yeah. But then based on this gadget, then I finally need to tell you, okay, how you finish the whole hardness. But then again, this one is just kind of standard, though it has some letters. Okay, so then suppose that you're given the CSP instance where like each constraint depends on A variables, and the alphabet size is R, and then the degree is D. Okay, so then our like final universe is just like this union of the universes for like every variable. Okay, so that's easy. And then how you like output? What are your final sets? Okay, so each set corresponds to like each accepting string over each constraint. Okay, so for each constraint that depends on like A variables, say x1 through xa, and then for each accepting string I1 through IA for that particular constraint. So then I'm gonna create one set in the following way. Okay, so one can see that the I1 through IA, so those are like each IJ is on the alphabet value. Okay, so so you can kind of see that those are like the colors that we discussed in the previous slide. But then actually I didn't tell what the J's are. Okay, so J is supposed to be like between 1 and D, so they kind of like, they must correspond to some degree. So then the way we use J is as follows. Okay, so we are in the beginning, we're gonna let each variable x to like arbitrarily order its D constraints. Okay, so if I'm variable x1, then this constraint is my first constraint, this one is my second constraint, so on. Right? Just like arbitrary ordering is fine. And then so that if I look at one constraint C, so then I look at all these variables I'm involved in, and then for each of the variable, so then I know that, okay, so for this guy I'm the 7th constraint, for this guy I'm the 5th constraint. So that's my J values. Okay, so the definition of JL is that the constraint we have right now, C, is my Lth variable's J Lth constraint. So J is between 1 and D. And then this is my final set. Okay, so based on the constraint C and then accepting string B, this is my final set is exactly union of the A of the basic sets, which corresponds to this Lth variable. And then, it should be an AL. Okay, so the value that we're gonna give to the variable XL, and then among them, the kind of the set assigned to the constraint C. Okay, so that's the final construction. It's almost the final slide, so let me just like let you stare at it. Yeah, you can kind of see that. So if I'm a constraint depending on these 2 variables, and then so I think I'm looking at the assignment that gives the 1 or like the blue color to first variable, and then red color to the second variable, and then if me as a constraint is the first constraint for this variable and the third constraint for this variable. So then yeah, by the set corresponding to this situation is the first blue set union third red set. So that's okay. So yeah, that's an introduction. And then once you can parse these like the symbols, then you can it's again not very hard to say that it's exactly approximately preserving. Okay, so basically, basically if you have if you have an assignment that satisfies every constraint, so then for each constraint there's like one satisfied string, and then just picking set corresponding to that particular accepting string will be all disjoint, because each variable will see only one color, and then each the constraints are like designated like different sets within the same color. Then that's it. Okay, so then we are done. In terms of extracting parameters, so we are starting from this hardness, a minus 2 d over a for the CSP instance when r is equal to d. And then now if you do this, then our final set size is just a times d. Okay, so then if you choose a to be 3, then you're going to get k over 9 hardness. If you choose a to be 4, then you're going to get k over 8 hardness. Okay, so we choose like the a to be 4. Okay, so that's the entire the reduction. Good. Okay, so that's it. Yeah, that's the whole thing. And then open problem, as I said, if you're interested, then one can ask what's the optimal constant. Okay, so k over 3, k over 4, k over 8. I mean, somehow personally for me, I think it's somehow the algorithmic barriers of k over 3 seems less artificial than the hardness barriers of like 4 and 8. I mean, hardness always proceeded in this like two-step route of going through CSP, which means that this like 4 and 8 always have to be the non-prime numbers. Whereas the k over 3, you can kind of see that because k over 3 is coming from the fact that, okay, so if you have a graph, then we have this like very nice the length bound for the in terms of number of edges and number of vertices. I don't know whether we can say the same thing for hypergraphs. Probably it might not be true. Okay, so somehow yes, for that reason, I feel that k over 3 might be slightly more natural. Okay, so k over 4, perhaps it will be technically really significant work, but then it might be possible to improve. Though I think you need to go beyond this like the framework. And then okay, so then of course these results. I mean, I kind of always assume that k is large enough constant, and then like ignore some like the little order terms in terms of k. But then one can still ask, okay, so there are like, okay, what happens if k is like 10 or like k is 5? These questions still, I think we can still follow the same route, and then of course there will be some bottlenecks, but then. I think this one, I mean, I don't know the answer to the question, but then one bottleneck is this. At least one thing, one question I have is, okay, suppose that, suppose that you're given like arbitrary T-regular graphs. Okay, so and T can be large. But then can you like subsample a D-regular graph? Okay, probably you need to make sure that, each edge is sampled with probably D over T. But then can you sample such a D-regular subgraph such that the distributions are negatively correlated? So that's because one place we lost we assume the k is large is again this like stupid the independent sampling and then like the truncating the degree. Okay, because like if you are naively doing it, then you gotta assume that k is large enough constant. But then if you just sample degree D regular graph, then you don't need to do it anymore. And then the question is like basically the only question is like, can you use turnaround in that setting? I think it's a very reasonable question. I mean I don't know whether like this is already known or not. Probably it's already known. But then I couldn't just find it. And then
the like standard way of sampling a regular graph of like sampling random perfect matchings.
Actually, but then the issue, it should be possible for every possible graph. Oh, actually, yeah. Yes, yes, yeah.
If it's bipolar, you're perfect.
Yes, yes, okay, good, yeah.
If it's regular, you can edge color the T plus 1 color.
Yes, yes.
And then just pick.
That's, yeah,
Losing a tiny factor.
good. Yeah, that's a very good candidate, yes. Yes. Yeah. I think, yeah, if you can do this, and then yeah, you can get some reasonable number even for like k is equal to 8 or like 12 or something, yeah. And then, yeah, the final question that I mentioned is like already like, I mean, yeah, now like k over 3 is already known, but then, yeah, can you have a kind of relaxation-based algorithm? I mean, local search is quite nice, but then it's quite embarrassing, I mean, at least for me, as a kind of relaxation enthusiast. Okay, just that it's we can't even like capture how to the simple local search. Okay, so that's it. All right, thanks.
Thank you. If there's any questions, please wait for the mic for the recording.
So, we are in 2006, and then they have this idea of random sampling to degree D,
Yeah.
and then they would also get this result.
I think the only bottleneck is I think so. The only bottleneck is
You use this means
yeah, this one. Yeah, of course. I mean, even this one was like 13, but then I guess probably, I mean, even in 2006, probably A over 2 or like something might have been known already. So
And then what would you get?
Yeah.
And then you would get omega k.
Yeah, some omega k. Yeah, I think so. Yeah.
Oh, okay.
Yeah, so it could have been done like 30 years ago.
So beside that, okay. Is it like, why do you need NP not in BPP versus NP versus P or quasi P, for instance?
Yeah, because like we are sampling. We are using randomness here.
But not because of the original assumption?
Yeah, original assumption is like just like NP hardness. I think we created randomness, and then I didn't think really seriously about the randomization.
Okay.
Yeah, probably. Yeah, I think everything kind of comes down to the random sampling.
Yeah, but that random sampling uses very few bits of randomness. No? I mean, quasi-P, you get it for sure. Then. Like just sample with log n wise independent, for instance.
That's, yeah.
But I guess we don't...
You took unit bound over exponential many assignments.
Oh, nice. So don't forget everything I said, yes.
So since the word quasi is repeating a lot of times, so this result is saying that it is hard to approximate the problem better than K in polytime. Mm-hmm. What if we ask quasi-polytime?
Yeah, I think, okay, so good. But then this is still like polynomial reduction. So I think you gotta believe, if you assume exponential time hypothesis, so you're gonna get some time lower bound for even, you can rule out the quasi-polytime algorithm as well.
You rule out much more on random.
Yeah. If you assume ETH, then any the less than like k over 8 approximation algorithm should run in like 2 to the poly n time.
So this subsampled instance seems like it could have a whole bunch more useful properties than just regularity. It seems like if you have any sort of bad structure in the graph that kills the hardness argument, you can sort of subsample and hope that no such structures remain. Mm-hmm. And so it seems like it's more broadly useful.
Yeah. It's the first thing you can try for any kind of hardness. Yeah.
Cool.
All right, so questions are dying down. We're out of time, so please let's thank him again.